Good afternoon, everyone. I'm Yibo Liu, and today I'll be talking about 3D vehicle asset generation from in-the-wild observations in autonomous driving. And I'll be introducing two papers. First one is MV Dipastia, and the second one is called VQA DIF. First of all, I'd like to I'm very glad to have this opportunity given by Professor Lindo to share my latest work here. And first of all, I'd like to briefly introduce myself. So currently I'm a fifth year PhD at York University, supervised by Professor Kim Shan. And previously I obtained my bachelor's and master's degree from Beihang University. And my PhD study actually began with research in robotic vision, control, and navigation. But since June 2021, I've been working as a part-time internship at Huawei, where I conduct product-oriented academic research related to autonomous driving. And currently, my research interests lie in the domains of 3D computer vision, AIGC, vision language, and embodied AI. So since I'm approaching graduation and seeking a postdoc position, hopefully we can find some good alignment with between my research and the research being conducted, and that will be conducted at TCIG. Okay, so now we move to the background. The reason why I want to introduce a background before presenting the paper is that I think by introducing the background, you can get the big picture of my research and better understand the motivation of my research. Also, I believe this slide contains some interesting knowledge that you might not be able to obtain merely through reading papers. It comes from my 2-year working experience in the industry.
One thing about looks like on Zoom, it's your presentation view. Maybe you can switch it. If you share the screen to the other, share the other screen. So maybe stop sharing and then share the other screen. Screen two. Yeah. Okay. Sorry.
So as we all know, an autonomous driving system Okay. So as we all know, an autonomous driving system is usually composed of multiple modules, such as the perception module, the planning module, and the decision-making module. And the models in these modules rely on training data to learn how should they react to real-world sensor observations. However, collecting training data is expensive, time-consuming, and labor-intensive. This is because to construct a large-scale training data set for autonomous driving, we need to follow such a pipeline. First, we need to build up the system or platform for sampling data. And usually for efficiency concerns, we need hundreds, even thousands of this kind of platform. And secondly, we need to hire people to collect data on the road and also from the government. And once the raw data is collected, we need to, again, hire a lot of people to process the data, such as filtering out bad data and performing annotation. So now let's consider such a situation. Suppose that we already have a running ecosystem, which is equipped with LiDAR sensor. However, at the same time, meanwhile, our system collected using LiDAR, the company decides to upgrade the LiDAR sensor from A to B. Maybe because the LiDAR sensor B is with lower cost, higher accuracy, but unfortunately, it has a different sampling pattern. So in this case, if we test our running system on the data collected using ladder center B, we will find significant performance degradation. And this issue is known as the domain gap. So to tackle domain gap, basically we have a few options. The first option is to redo the entire process data collection. So the advantage is that the performance is guaranteed because we didn't change the pipeline. But the shortcoming is that this solution is expensive, time-consuming, and labor-intensive. So the second option is to apply the domain transfer technology. For example, this time we only needed to construct a small-scale data set and then apply the domain transfer method to fine-tune the model being used on this small-scale data set to mitigate the performance degradation. So the superiority is that this time the money and the time can be saved. However, the shortcoming is the performance degradation still exists. And from an academic perspective, the second option actually sounds more promising or advanced than the first option. But in real industry, people actually prefer to choose option one since the performance is guaranteed. And this is because in real world, trivial performance degradation could lead to traffic accidents. I know that our original intention is to save money, but suppose that some traffic accident happens, this could put the company in big trouble. So given the superiorities and shortcomings of these two options, some leading scientists, such as the founder of Wabi, say that there's actually a third option, that is to build a high-fidelity simulation platform. So in this type of platform, different weather conditions, illumination levels, and road conditions, and different sensors and different driving behaviors can be simulated. So suppose that we are faced with the hardware changing issue I mentioned earlier. We only need to replace the sensor in the simulator, then generate a new large-scale data set to train our models one more time. So the issue solved. And the ultimate goal of developing a high-fidelity simulator is to enable this one. That is, models trained in the high-fidelity simulator can be deployed to real world directly without any performance degradation, but know that this is just the ultimate goal. And all the companies, they are working towards this goal. And we usually split the task of constructing a simulator into two subtasks. The first one is background reconstruction, and the second one is foreground reconstruction. So background objects usually refer to static objects such as the road, trees, and buildings. And foreground objects are vehicles, pedestrians, and cyclists. So now we understand why the collection or generation of 3D vehicle assets is crucial to developing a high-fidelity simulator, and why it is important to autonomous driving. Because the 3D vehicle assets shown here are the most important foreground objects in the simulation. So the second keyword in my talk is in the wild. In the wild. So the difference between in the wild observation and the observation in a laboratory setting or in a controlled environment is that in the wild, observations are usually with severe noise and occlusion and distortion. So it is more challenging to handle in the wild observations. All right, so now we move on to the first paper, MVDeepSDF. And the full title is Reconstruction in Autonomous Driving. So in this work, our objective is to reconstruct 3D vehicle shapes from partial LiDAR point cloud. And in particular, we choose to use the implicit modeling. So compared to explicit modeling, such as shape representation based on point cloud, 3D meshes, and voxels, implicit modeling represents the 3D shape with a continuous function, such as the sign distance function. And this kind of shape representations force mesh extraction at any resolution. And this point is crucial for developing simulation. So that we're going to simulate some high resolution LiDAR in the simulator. The resolution of the mesh. This is the reason why we choose implicit modeling as our solution. But the problem is previous methods only focus on reconstructing the 3D vehicle or focus on object reconstruction from a single view observation. And also they are designed to deal with observations in a controlled environment with trivial noise. So suppose that we test them on real-world observations, they can only produce results with low fidelity. So in this work, we propose a novel framework named MVDeepSDF to exploit the noisy and sparse real-world LiDAR partial point clouds. And in particular, we exploit the multi-swept LiDAR point clouds. This is different from previous method. And we simplify this task into an element to set feature extraction problem. And to achieve this objective, we infer an optimum estimation of the 3D shape described in the implicit space. So this is the overview of our framework. There are 3 main steps. The first one is pre-processing. Second one is optimum latent code prediction. The third one is 3D mesh extraction.
What is the LiDAR suite?
Here?
Are these different, like, time samples?
Right, because as the ego vehicle moving, you could observe the vehicle from views.
So you assume there's some sort of track.
Yeah. Yeah.
You expect.
Yeah, because usually in the data sets such as Waymo KT, the multi-wheel information of the vehicles are available because the tracking labels are available.
Yeah, got it. And they're registered to each other? You assume they're registered?
No, they are not registered. But if you want, you can use the bounding box to stack them into one frame. But this will lead to another issue. I will present this later on. So our baseline model is DeepSDF. So for DeepSDF, suppose that we are given a 3D querying position, which is represented by X, and one-dimensional latent code, Z. The function of the DeepSDF decoder can output the SDF value of this querying point. So suppose that this querying point falls on the surface of this object, then the SDF value will be 0. And this figure shows the result of DeepSDF under different given partial point cloud. So to utilize the multi-swap information, we first analyze the consistency and the complementarity in the latent space. We propose that for each latent code, for each individual latent code, it is composed of 3 components. The similar component, the different component, and the error component. The similar component refers to the component that has some shared information with refers to the shared information between the given latent code and the ground truth latent code. And we think that there are 3 situations. First, suppose that the given partial Planck clouds are case 3 and case 4. In this case, their latent codes have no shared information, so they have completely different information. And suppose that the given partial Planck clouds are case 2 and case 3, that is, they have some overlapping regions, but their Planck clouds are different. So that is, they have some similar information, but the information is not redundant. And for the third situation, suppose that a given partial Planck clouds are case 1 and case 2, the information is actually redundant. So our objective is to extract the yes, please.
What does it mean to take the intersection of 2 different variables?
I'm sorry, what?
What does it mean to take the intersection of 2 different variables? Sorry, like when you write that I intersects that GT, like you refer to labels?
Yeah, this means the shared information between the 2 latent codes.
But how do you actually measure this? Like how do you actually?
So I will introduce how we achieve this in the next slide.
Okay.
Yeah. So our objective is to extract all the similar information as shown here, and also predict the uncaptured regions by the observations. So this is our objective, and we design an architecture to achieve this objective. So our inspiration comes from the classical QuantNet, which is a impactful framework for Planck cloud classification and segmentation. So the QuantNet learns a global feature representing maybe the class of the Planck cloud. And in particular, the input is a set of 3D Planck clouds. And then Planck cloud uses a shared MLP to extract the 3D point features for the first step. Then it utilizes a max pooling layer to aggregate the 3D point features and transform it into a set feature. So we abstract this pipeline into a general pipeline. So that is, the input is a set of elements, and our objective is to learn a set feature. So to do this, we first use option 1 to extract the element features. And then we need to apply option 2 to transform the element features into a set feature. So in particular, in our framework, the input is a set of 3D partial Planck clouds. And we apply shared PCN encoder and the deep SDF decoder as operation 1 to extract the element features, which is actually the concatenation of the global feature produced by shared PCN encoder and the latent codes. Then for option 2, we apply an average pooling. We apply the average pooling operation to transform the element features and also mapping to transform the element features into an instance feature, which means the feature of this set. So in terms of your question, actually we use the shared PCN encoder to learn, like to analyze for the given partial Planck cloud, which parts for which region is captured by this point cloud. And correspondingly, as for its for the latent code, which part of the latent code should we trust, or how to extract the part the part that should be trusted from the latent code. Basically, that's the intention of this architecture. And for model training, we apply a curriculum learning strategy. That is, for stage 1, we only train the PPSDF decoder to gain some priori knowledge of vehicle structures. And then for stage 2, we train the shared quantized encoder and the mapping layers to learn how to optimally estimate the ground truth latent code. And when preparing the training data, also to reduce the domain gap between the training data and the in the wild observations, we adopt a technology called PCGen. That is, we place a virtual LiDAR around the object to simulate the LiDAR point clouds. And we can, as you can see here, we can set the parameters of the LiDAR to simulate different data sets. And we conducted both qualitative and quantitative experiments on 2 data sets, that is KT and WeMo, and we apply asymmetric chamfer distance and recall rate as a matrix to evaluate our model. As you can see, our model yields best performance. So as for the issue raised by Professor Lindo earlier, if we start the point cloud using the annotation information or tracking information into one frame, the issue is that the noise is also aggregated, and this implicit modeling-based methods are quite sensitive to noise. So as you can see, the results are with even worse fidelity than the results of a single frame. So here, plus MS indicates we use the stacked point cloud as an input.
One question on the method: how do you get for the auto decoding? Slice randomly, or typically the way I understood how SDF works for this task is you optimize the latent code so that the SDF fits the point cloud observations that you have. In this case, it's
the same way. So it's shown here. Actually, for pre-processing, we import the point cloud into the SDF and then obtain the data code here.
Oh, I see. Yeah, but that's an optimization, right?
Yeah, right. Optimization based.
Okay.
Yeah, got it. And note that for this method, they are single-shot based structure method. So in this table, we only compare with the best result.
The DSDF baseline is on one partial scan, or how do you incorporate?
Suppose that for a given vehicle, there are, let's say, 10 observations.
Yeah.
So there will be 10 results, reconstruction results. We only compare with the best one, because we can compute the matrix for each one.
Got it. Yeah. Okay.
Yeah, sure.
It looks like some of the graphs you presented are not any standard, like this is one of the parts. How do you see the chamfer distance?
That's why we applied asymmetric, not the real complete chamfer. That's like a one-way chamfer distance. Yeah. We use this matrix because MATLAB, which was proposed by previous Uber AGT, that is the current Wabi. They have a similar paper, and they they adopted this matrix.
Okay.
Also, so in this slide, we also report comparison between a non-learning approach. So one may think that since the latent code is available, why don't we just compute the mean of the latent code to as the optimum estimation? So this example shows the reason. So as you can see, the mean is just a linear combination of the results, and in contrast, our model can produce a more reasonable result with higher fidelity. And the MVT-PassDL framework is actually a general framework that can be extended to other, such as SOFAST sectors. Yeah, basically that's all for the first paper. So the second paper I'm going to introduce is VQA-DIFF. The full title is Exploiting VQA and Diffusion for Zero-Shot Image to 3D Vehicle Asset Generation in Autonomous Driving. So in this work, we aim to create novel views of vehicles from in-the-wild observations. So previous method only learn image to novel view generation using the RGB information in a natural or a latent space. So this leads to their poor zero-shot prediction ability when handling in-the-wild observations. And in this work, we propose VQA-DIFF, which utilizes the powerful zero-shot prediction ability of the visual question answering model and the rich structure and appearance generation ability of diffusion model. This help us to create novel views of any unseen vehicles in the web. So the contributions of this work are presented as follows. So first, we propose a novel generative model named VQA-DIFF to create photorealistic 3D vehicle novel views from challenging in-the-wild observations. And secondly, we propose a multi-expert diffusion models strategy, which can generate multi-view vehicle structures better than single diffusion model. And finally, we conduct both qualitative and quantitative experiments, popular data sets, demonstrate that our method achieves state-of-the-art performance. So again, this is the overview of VQA-DIFF, and there are three components. One is the VQA model. Second one is multi-expert diffusion models. Third one is the control net. Okay, so now I'll be introducing the motivation. As I mentioned, previous methods rely only learn from the RGB information to learn novel view generation or synthesis. And they fail to deeply understand the features of vehicles using real-world knowledge. So as you can see here, if the input observation is an occluded image, it fails to understand that this is a vehicle, and this vehicle is just occluded. Its geometry is not like this. It only tries to use the priori knowledge it gains from the image to 3D data set to reconstruct the shape. So it will generate some low fidelity results. And actually, it is very tricky for this method. I mean, the method follows an image to novel view learning manner to develop zero-shot prediction ability because there lacks an ideal data set collected in the real world, which contains a sufficient number of car models, viewing angles, and complex occlusion cases. And in this work, we intended to learn from deeper understanding of vehicles to achieve better novel rendering performance. So the reason why large language model or VQA models have robust or powerful zero-shot prediction abilities because they are trained with a numerous amount of data. For example, large language models are usually trained with billions samples, and for VQA models, they are trained with hundreds, millions of samples. So they have gained real-world knowledge, and they have a deeper understanding of vehicles. So first, I'll be introducing the VQA processing. So we through prompt engineering, we design an appropriate question to extract the useful information from the raw image. Specifically, we use the feedback from text-to-image stable diffusion, and we tune the question based on the feedback until the answer or the output of stable diffusion is consistent with the given image. So the final design question is, what are the model, manufacturer, production year, and the main features of this vehicle? As you can see, if we ask the VQA model this question and feed the final answer to the stable diffusion, we will obtain exactly the same vehicle as the given image. And for structure generation, we propose an multi-expert diffusion model strategy. This strategy or this framework is composed of a text-to-image diffusion model and 4 image-to-image diffusion models. So this model is responsible for transforming the prompt into 4 views. And then we transform each of these 4 views into another 4 views using the image-to-image diffusion model. That is to say, there are 16 views in total. And since these views, they are closed images, you can use them to do whatever you want, like NURB, 3D Gaussian, splatting, and many other downstream tasks. So seeing this framework, you might have 2 questions. The first one is, why did we choose diffusion model? So this is because a pre-trained diffusion model has rich priori knowledge vehicle structures. Namely, if we provide the stable diffusion with a prompt like a Tesla Model 3, as you can see, it can produce many photorealistic observations of the Tesla Model 3 observed from different views. However, please note that these images, they are not 3D vehicle assets because we cannot control the object pose in these images. But we found that actually by fine-tuning on synthetic data sets such as ShiftNet, we can inherit the priori knowledge of vehicle structures. As you can see here, if we provide our fine-tuned model with a prompt like the Tesla Model 3, it can generate the multi-view structures of this view. And please note that the ShiftNet dataset actually doesn't contain the car models developed in recent years, such as Tesla Model 3. So that is to say the model actually never have never seen Tesla Model 3 in the training data. However, it is able to generate some multi-views of Tesla Model 3. And the second question might be, why did we design the multi-expert diffusion models? This is because our framework can generate the multi-views vehicle structures with better image quality and better consistency. We also conducted a application study regarding this. So for appearance generation, we apply a subject-driven structure control generation. So as you can see, actually we still use the powerful VQA model to deal with the appearance information extraction problem. But this time we only use the multimodal encoder of the VQA model. So this encoder can transform the raw image and the answer of the VQA model, that is the prompt, into a feature that can be utilized by the unit of Blip diffusion. And we also transformed the vehicle structure generated by our multi-expert diffusion models into some edge maps. And then we utilize control net to transform the structure condition, provide the structure condition to the Blip diffusion. And then the novel view is generated by the unit Blip diffusion. That is to see the novel view, the generation of the final novel view is controlled by the VQA result, the raw image, and the vehicle structure technology. So we conducted experiments on three popular benchmarks, including Pascal 3D Plus. And our competitors are Dream Gaussian, 0123, and NeurFarm image. So as you can see from here, this vehicle is actually with distortion due to maybe a short focal length. So as I mentioned, previous image to 3D model, they fails to learn with a deeper understanding of vehicles. So in this view, since the trunk of this truck looks tiny, so 0123 thinks this vehicle is something with a tiny trunk, which is with low fidelity or bending, right? And so for methods like Dream Gaussian, they rely on the prior knowledge of models like 0123 to finish the reconstruction through so-called scored distillation sampling, SDS. So since their baseline model fails to provide the correct null views, they actually cannot handle in the wild observations at all. And for this method, NeurFarm image, it is released by Google and published in CAPR 2023. It learns on real-world dataset directly, that is a Pascal 3D dataset directly, and it contains some, since the dataset contains some cases with occlusion, so it has the ability to deal with occlusion to some degree. But again, since it only learns in an image-to-image manner, it ignores the arc between the body and the trunk. So it actually produces an SUV, which is a wrong vehicle model. And this slide shows the result on Waymo. And as you can see, these two observations, they are highly occluded. But our method can still produce high fidelity novel views. Oh, I forgot to mention, for matrix, we apply text to image and text consistency score, clip similarity, FID, and VQA score. And as you can see, our method outperforms previous state-of-the-art models. And this slide shows the result on observers. Moreover, our model can cooperate with text-guided style transfer models, text-to-image models, and text and shape-guided object imprinting models. For example, by collaborating with style transfer models, we can transfer the pin of the vehicle. That is, we can generate a new reference image, then generate 3D vehicle assets with different pins. And also, we can generate desired vehicles merely based on prompt. That is, we provide the text-to-image model with a prompt, let it generate a reference image, and then we can create the corresponding 3D vehicle assets. Moreover, by collaborating with text and shape-guided objects imprinting models, we can do some fine-grained generation, such as, this is the raw image, the given image. We can use the imprinting model to, for example, add a rear spoiler to it, then generate the 3D asset. Or we could change the pen or the colors of the different parts of the vehicle. And we can also control the geometry of the vehicle. So the proposed method can be extended to other generative objects. So here we show a case of motorbikes. As you can see, our models can be, our VQADIF can be extended to motorbikes. And finally, we conducted many population studies. For example, we studied the effect of multi-expert diffusion models. We also studied the effect of prompt engineering and the effect of different VQA models and the effect of training data and the control net. Yeah, that's all for the second paper.
Sorry, maybe I have a somehow silly question, but did you test the difference between, you just use the identified text and use the text plus branch truth? Is there a difference? Just like, if the generation is just it's a fixed perspective, I think the ground truth, given the prompt, ground truth may be not important.
Can you please repeat your question?
Yeah, because most cars are just industrialized models, so maybe because they are also already included in some of the training efficient models.
Yeah.
So is the ground truth still important? Have you tried the difference between just use of text and ground truth plus text?
I feel like this figure addresses your question to some degree.
Yeah, so because I was wondering, the main goal is you use the ground truth plus the VQA results.
Mm-hmm.
I just want to know, is there really substantial difference between just using text?
Just the use text. Mm-hmm. Yeah, that's really interesting, but for task of null view rendering, suppose that we want to obtain some 3D asset with similar appearance with the input. If you say we only use the text, it will be very challenging because I think it's very challenging to describe the illumination, reflectivity regions using text.
Yeah, actually, I just want to ask, did you try about the difference? I don't think there will be substantial difference. I just wondering if you have some tries before me.
So actually, we did a relation study like what we just said in the rebuttal, but I didn't include that in this slides. But I can show you maybe later.
Okay, well maybe we can thank you. Other questions? I had a few questions I can ask. So I was wondering about the first project. You motivated the whole line of work with part of the motivations the fact that point clouds are noisy or incomplete. So were any of the results that we saw on in the wild LiDAR scans?
Yeah.
Nice.
So we tested all the models on KT and Waymo, which data set kind of cool.
But okay. And but I guess you can't get the quantity.
That's a good question, but
Just to evaluate. Oh, I see.
actually, we can. Just now I mentioned this paper. It's a work, mainnet. It's a work from Federal Hill School. So they are dealing with a similar problem, but they were only focusing on single shot construction.
Yeah.
So as you mentioned, the ground truth is actually not complete. So it might not be able to compare the reconstruction result with the ground truth, what we do in a laboratory setting, like computing the chamfer distance. That's why they utilize the asymmetry chamfer distance. That is one-way chamfer distance, and the recall rate to evaluate their models. We will follow the
I guess the ground truth is also noisy, right?
Yeah, right.
So it's so how much can you trust the metrics, I guess? Right? Like the reference itself is noisy, so
yeah. I feel like it is definitely beneficial to have you can present a 5 or 4 matrix, show that the model still shows the sort of performance. The result is solid. But for this task, since to be honest, not many people, especially for people in the academia, they are concerned with real world applications. So obviously the matrix in this field weird. So that's why we'll only tried those two. But yeah, we did. I mean, previously we also thought about the same question, which we just read. But yeah, but as I mentioned, the available or alternative. So there is a potential.
okay, maybe I can ask one more higher level question, which is, do you think it takes, or what is missing to go from what you have now to this vision of seeing the reconstructed assets in simulators for Armstrong?
Okay.
Whether, for this project or the next one, which is a bit closer towards you mentioned at the beginning.
So currently, I think although the background papers, it is the same. That is, we are working for developing a high fidelity simulator, but I feel like these two papers are kind of different papers. Because the input of the first paper is LiDAR transcode. The input of the second paper is images. So I feel like suppose that we can fully utilize all the observation obtained by an Eagle system, that would be better. And also, we are only in these tools, we are only dealing with regular vehicles actually. So it would be an interesting future work if we could deal with the vehicles that is not very common. And this is definitely also very beneficial for simulation. And the last point I want to see is that these tools, they are just like the prerequisite to constructing a simulation. Because even if there's 3D assets 10, we still need to design their driving behavior or their occlusion or distortion in the, so we have many downstream tasks to be done to complete the simulation.
Yeah, it seems like you need like just a good couple other things that keep in mind. Like you need to be able to model material properties, so you probably
Yeah.
relate them in the environment. You have to like rig them so they can somehow be animated and move.
Yeah.
The wheels would spin. Yeah, so but it's a good first step here. Okay, other questions? Okay, well, yeah, let's thank Ivo again.